Thank you. So for this last lecture, we're going to change settings a little bit. And so that would be the fourth part. And this is finally Lie theory day. So now we're going to start, as we like to start our sentences, by saying that let G be a semi-simple group. And whatever over R. You know what you add.
Semi-simple group over a totally disconnected local field?
Yeah, over, exactly. You'll get it from context, I think. Yeah. Yeah. I could bring it back to SLN, if you're. Yeah. Okay, so we're going to be discussing the setting of not just what flag manifolds are, but also sort of how I like to think of them, and also something that we'll call transverse flag spaces. So we'll start with a few definitions, as Lie theory always asks you to do. So we'll be considering hyperbolic elements of the Lie algebra. So an element x in the Lie algebra of G is called hyperbolic if the adjoint map of G is diagonalizable over R, or R split, if you'd rather say. And whenever you have a hyperbolic element, so I'll just write G hyperbolic, this will define a Lie subalgebra of G, which is Px, that is just the sum of the eigenspaces for this adjoint action, but for non-negative eigenvalues. And we'll also define a group from this, which would be the normalizer of Px, so the sets of G in the group, for which the adjoint action of G stabilizes Px. And then it's a not so obvious fact from the definition that, well, the easy one is that Px is so that's a fact. Px is a Lie subalgebra. Of G. The other, even easier one is that big Px is a closed Lie subgroup of the group G. The less obvious one is that the Lie algebra of this group is this Lie algebra Px. And it's simply the fact that this Lie algebra Px has the property of being its own normalizer in the Lie algebra G. All right, so what we will call a parabolic subgroup or subalgebra will be one of these subgroups, one of these subalgebras. So let's say P inside of G is a parabolic subalgebra and I will insist here it means that there exists some hyperbolic element x with P is Px, but this x is far from being unique. Right? There are tons of x's that will work. And the same for a group. P in G is a parabolic subgroup. If it is Px for some x. And the last definition here will be a flag manifold for G and that would just be a homogeneous space isomorphic to some G mod P, right? So some G homogeneous space right, so stabilizers are parabolic subgroups. And we may well pretend to be working with some very abstract groups. In the end, we'll always be thinking about SLN. So that's the one case to have in mind. And in that case, being hyperbolic just means that X as a matrix is already diagonalizable over R, right? So X in Right, so if you want to understand what are the possible flag manifolds, you'll just have to look at these at diagonal matrices, right? So you can just pick X to be something like, we'll write it by blocks to include repetitions. So it will be a first block with some X1s a bunch of times, up to some XRs a bunch of times. And we'll assume all the x's to be arranged in this order and dimensions to add to the total dimension D. And of course, you should ask, this is a Lie algebra, so the trace should be 0, so there's another equation to be satisfied. Right, and now this the parabolic subgroup in this case is just upper triangular matrices in the block decomposition corresponding to this, right? We have zeros here and a bunch of things over the diagonal. But when we talk about flag manifolds, usually you don't want to, if you're working with SLDR, you don't want to think about flag manifold abstractly, you just want to actually realize them as flags, right? So you would have a flag manifold behind this, which is what we could call f from D1 to dr of RD. Right, this would be spaces V1, V2, up to V. Actually, you only need R minus 1. I'll search that V1 plus, sorry, V1 is included in V2, included in VR minus 1. And the dimension of V should be corresponding to the sums of the dimension D's that go up to there, right? So V should be the corresponding to the first block, so this is in the Grassmannian of dimension D1. But the second V is the one that is preserved by the parabolic subgroup. So like V2 should be corresponding to the sum of the two first, or the thing spanned by the first rows in the two first blocks. So this is in the Grassmannian of dimension D1 plus D2, and so on. Right, so if you look at this flag manifold, this will be, you take the flag corresponding to this block decomposition, its stabilizer will be exactly this px. Right? Right, so it is quite nice to have a simple description of flag manifolds in general. And you don't want to think about any hyperbolic element X, maybe just a few of them. And with SLN, you'll definitely want to think about these flag manifolds that are actually flags. But if you're doing this with a general semi-simple Lie group, there's also another way of stating this, which is quite nice. So we'll start by defining what we call a standard flag manifold in general. So now we're back to G semi-simple, and a standard flag manifold is a way of choosing one of these homogeneous spaces with stabilizers Px. And what you can do is define from any x hyperbolic. This will be the G orbit of Px. Right? So this is a subset of a Grassmannian of the Lie algebra, of the spaces whose dimension is P of the dimension of Px. Right, and so if you were to do this for SLD, this flag manifold over there would correspond to the set of parabolic subalgebras that are stabilizing a flag of this type. Exactly right. So that's a remark, is that any flag manifold for G is isomorphic to a unique standard flag manifold. By isomorphic, I always mean like G equivalently diffeomorphic. Right, and this isomorphism is pretty tautological. If you have a flag manifold F, this will be going inside some F standard, some parabolic in some Grassmannian of some dimension D. Right, and these elements are parabolic subgroups. Parabolic subalgebra, sorry. So you take a point X in your flag manifold, and you just look at the Lie algebra of the stabilizer of X.
Yeah. I have an issue with the sentence in yellow. So you are up to isomorph, G equivalent isomorphic, you have only finitely many flag manifolds, but you have uncountably many X.
Yeah, still. There are only finitely many standard flag manifolds. That's the. I could actually also add here, it's uniquely isomorphic, actually. That's even better. Yeah, there are only finitely many standard flag manifolds, and they don't correspond to orbits for the adjoint actions. They correspond to orbit types, right? So there are many x's, uncountably many x's will have the same standard flag manifold. Right. If you just know what your flag manifold is, you don't know what some. Even if you fix a point of your flag manifold, so then you have the stabilizer, which is a parabolic subgroup. For a given parabolic subgroup, let's look at the definition here. For some p, there are many x's for which p is equal to px.
Yeah. I don't understand. What is the flag manifold?
A flag manifold, in general, it's a homogeneous space whose stabilizers are parabolic subgroups.
Yeah, but I mean in the standard flag manifold definition, because fx, you say it's a subset of the Grassmannian.
Yeah. So you're looking at, if you choose some x hyperbolic element. So this px, you see it as a vector subspace of G. Right, so it's an element of some Grassmannian of G. And now you look at this G orbit, because G is acting on all Grassmannians of G by the adjoint action, right? So maybe I should have said add of G acting on this. Right, and so this is a subset that happens to be a closed compact submanifold.
And so is it easy to see that it is a flag manifold?
It is easy from the fact that I said, which is not an easy fact. The reason why the stabilizer of Px is the subalgebra is the group Px is exactly because Px was defined as the stabilizer of the Lie algebra.
So it's an homogeneous space with stabilizer and Px. Okay.
A flag manifold in general, yeah. So this is a homogeneous space with stabilizer Px. Exactly. Yes.
So to you, a standard flag manifold of G is a closed subset of craft manifold of the algebra.
Yeah.
And so when you talk about uniqueness, you're talking about equality.
Yeah, it's really up to equality. It's not up to isomorphism, and that's why I'm saying it. So it's uniquely isomorphic, actually. That's the addition here. Understanding this this is not just me spending a little bit of time at IHES and going full Grothendieck and having everything being functorial or whatever. This is really something that has helped me to understand how to work with flag manifolds, to actually treat them as something really natural and canonical.
By the way, what's the stabilizer in the algebra?
The stabilizer, this is Lie algebra of the stabilizer. You say, right? Yeah. Yeah. Okay, but if you are to work with, if you're given an explicit Lie group with its Lie algebra, you may have a better description of these standard flag manifolds. But I'm just saying that even in this abstract setting, you have one description that at least I find nice, as these closed orbits in Grassmannians. Right, but if you're working with SLD, you definitely want to ditch this this thing and just work with flag manifolds as they were meant to be. Yeah. And so maybe what will clarify things is when you talk about this classification, right? Because the usual way of defining standard things when it comes to parabolic subgroups of algebras is to use a restricted root space decomposition here. So right, so here I'll just get my G, decompose it as some A plus M plus some of some G alphas. And I have to say what these things are. So A will be a Cartan subspace, or like the Lie algebra of a maximal split torus. M will be the zero eigenspace. It's defined by the fact that it commutes with M and that it's orthogonal to A for the killing form. You actually don't need to fix a Cartan decomposition to define all these things, by the way. You don't need to fix a maximal compact subgroup. And these are the restricted root spaces. Okay. Now we're also going to fix a simple system, delta, and with the associated Weil chamber A plus and in A. So where all these roots in delta are non-negative, so this will be a closed Weil chamber. And well, then if you know about the theory of parabolic subgroups, you'll know that there is a correspondence between parabolic subgroups up to conjugacy and subsets of this delta, right? So if you have a subset delta, theta, and delta, what you do is you consider some x theta in A plus such that the set of simple restricted roots that are non-zero on x theta is exactly theta, right? So this is a subspace in the cone A+. And then you can define everything depending on theta, like f theta. You can define it as f of this x theta. Same for p theta, and so on. Right? And this does not depend on the choice of this x theta. I think this what was the confusing thing earlier. Right, but really the difference between working with this description of standard parabolics and working with standard flag manifolds in general. So what I should say here is that every standard flag manifold f is equal to f theta for a unique theta. Right. Because if you're working with parabolic subgroups, you'll get that a parabolic subgroup is conjugate to a unique standard parabolic subgroup. But there's not a unique conjugacy. There's not a unique isomorphism going from one to the other. And that will tend to mess up things when you're working with them. But the flag manifolds are actually equal here. Right, so this is, in my opinion at least, a description that I like. And something else that you'll have that we'll probably forget and eventually come to later is the notion of domination between flag manifolds. So if you have two subsets, theta and theta prime, you can wonder if there is a G equivalent map from one to the other. And now with this restricted root space, there's a nice description of this. This is equivalent to having theta, which one is smaller? Theta prime, including theta. Right? If you think of SLN, you'll have take of the two extreme examples, take one to be just theta to be the whole delta. So then your flag manifold will be full flag manifolds. And you take theta prime to just be, say, the corresponding to the projective space, just be one Grassmannian in general, so be just one element here. And you'll always have these projections for the full flag manifolds to any Grassmannian. It does mean that this smaller thing here is included in theta. Right, so you also get this thing that there are two interesting types of flag manifolds that come out of this picture. One of them is sort of the smallest ones, which correspond to just singletons here, theta prime in delta. Those are the maximal parabolic subgroups. And there's the other one, which is theta is the whole delta, and that corresponds to full flags for SLD and to a minimal parabolic subgroup in general.
Just for sanity check, can theta be 0? Can it be empty? Yes.
If you want it to be empty, yeah, and then and then your flag manifold will be just 1 point. Yeah, it is a homogeneous space. Right, so
You only require smoothness of this map.
you don't even need to require actually. It's just a map G equivalent, and then yeah, maybe yeah, right. Yeah, continuous. I'll give it to you. Yeah. And this is not an easy fact. Right, this has to do with the fact that if you take a parabolic subgroup containing a standard one, is also a standard one, and there's something to be said there. But yeah, I know there are a lot of that green book of Knapp enthusiasts here, so you probably already know about this stuff. All right, so the second type of homogeneous spaces that I want to work with here are the transverse flag spaces. Okay. All right. So if we go back to a hyperbolic element x, we're going to define a few more. Okay, one more Lie subalgebra that I'll call Lx. That will be defined as the centralizer of x in the Lie algebra, so things that commute with x. And capital Lx will be the same in the group. Right, so these are what we call Lévy subgroups and Lévy subalgebras. So and these Lévy subgroups were already there in the picture because you have another fact here that could possibly be a lengthy exercise, but I don't think so. Lx is the intersection of Px with P minus x. That's another way of studying it. It's easier on the Lie algebra level than it is on the group level. Yeah, I mean, that's what Lie algebras are for, actually. Right. So now from this, we'll have a general definition in flag manifolds. If you have F plus and F minus, two flag manifolds for the same group G, and you have some points in there, x plus, x minus, and we'll say that one, oh, let me change my letters here. I feel like my small x's and large x's will be really confusing. So let's call them F for flags, F plus and F minus. And we'll say that F plus is transverse to F minus. That's a definition. If there exists some hyperbolic element x such that F plus, the stabilizer of F plus is Px and the stabilizer of x minus is P minus x. Right, so stabilizer in G of F plus minus is P plus or minus x. Another way that you might want to describe it, so this will define the set of transverse pairs in this way in the product. And yet another fact is that this is the only open G orbit in the product. Right, in this space of transverse pairs, we'll call it the transverse flag space. And the last definition here, which that we'll call two flag manifolds, they could very well be empty, right? The empty set is open. Is it a G orbit? You'll decide on this. We'll say that a flag manifold F plus is opposite to F minus if there actually are some transverse pairs in there. Okay. All right, so there are many ways of describing this. You can see also this as living somewhere in the boundary of the symmetric space and saying that you have geodesic going from one to the other. This is, at the moment, my favorite way of describing it. It could very well change within a few minutes. So maybe some some example before stating a bunch of facts. If you look at SLD, right? At SLDR, if you look at some flag manifolds, so say F plus is a flag manifold corresponding to some dimension D1, dr. F minus is corresponding to some D prime 1, D prime R. Some actual flag manifolds. Sorry?
Same R?
Yeah, R prime, you're right. Thanks. So when are these opposite? They're opposite exactly if they have compatible dimensions. In the sense that maybe I should have added my dimensions in increasing or decreasing order to make this unique, by the way. Yeah. So then you'll have that F plus is opposite to F minus if and only if, now I need to get it right, so R is R prime, and if you look at the list from D1 to dr, they will be D minus D prime R, D minus D prime 1, I think, right? Something like this. And the general picture is that it has to do with the opposition involution on roots. Right, so opposite for SLD just means that if your parabolic subgroup on some side, on one side is upper triangular matrices in a block decomposition, then the P minus X will be lower triangular matrices in the same block decomposition. And then the standard, the transverse flag space will correspond to, well, the LX in this case, let's say, will just be block diagonal matrices, right? So G1 up to GR with each GI is in GL of DI and the product of the determinants is 1. Yeah. Yes?
I'm a bit confused. So your definition of transverse implies that the parabolics need to have the same type?
No, they're the opposite type.
No, in the sense of the vertices you circle on the diagram?
So if you do it with subsets of simple roots, this exactly means that one corresponds to a theta and the other one to the opposition involution applied to theta.
Okay. Yeah. You said it was allowed to be empty. Right. It's transverse flag.
Oh, sometimes it will be opposite to itself. Right. Yeah, and also, yeah, it's allowed to be empty. Like the case where it's non-empty. So let me say F. So in general, with the standard description over there, F theta is opposite to F theta prime is equivalent to saying that this theta prime is the opposition involution applied to theta. In SLD, this opposition evolution sends D1 to dr to d minus dr to d minus and d minus d1.
Sorry, I'm a bit confused. So in the in the top blackboard, you cannot require d1 to dr to be the disordering, right? Because you require x1 greater than x2 greater than xr. Then we don't know anything about d1 to dr. Only the sum is d.
So I think these are two. Okay, you should see it as first fixing the d's, then choosing some x's.
So you want x to be the right ordering because so that p can be up the triangular.
I think it means the inequality is d1 less or equal to d1 plus d2.
Yeah.
Yes, you're absolutely right. So yeah, so actually we don't. Yeah, thanks. Yeah. Yeah. Okay. Well, just ignore that that thing. Sorry.
Also, I'm confused with that in those conditions. Like, does the sum match? Like, if I sum u1 over dr and u1
well, let's say that it's something like that. So you'll have to make sure of what the exact formula is. I'm pretty sure this is the one. Maybe you'll have to. So you think maybe you have to replace with the corresponding formula where expect of the instead of the d's you look at like d1 plus d2 up to di every time. But I still think this is the right one. Wait.
I think the partial sums match.
What? Yeah, yeah. We'll have to. Yeah, I agree that there might be a problem there, but nothing that can't be fixed. Okay. All right. Sometimes this abstract setting is easier. Okay, so now you get that from these characterizations, actually, with standard parabolics, you get that a consequence of all the facts that we've stated is that every flag manifold is opposite to a unique standard flag manifold, or to a unique isomorphism class of submanifold of flag manifolds. Right, so fixing one flag manifold or fixing a pair of opposite flag manifolds is essentially the same.
At the level of standard flag manifold, in this description over there, is it just looking at the one like fx and f minus x? Or?
Yes. Okay. Yeah, for standard if another way of saying is that f plus is opposite. I mean, this is almost the definition, right? It is the definition. To f minus is equivalent to there exists some hyperbolic element x with f plus isomorphic to fx and f minus isomorphic to f minus x. Yeah. All right, but the important thing is that you don't just, you have this notion of not just of this opposition relation between flag manifolds, but also of the transversality of pairs inside them. Right, because by now you should realize that some of these notations are exactly the same that I've used with P of V and P of V star earlier. Right. And so using these exact same notations, you can define the same objects that we had to define Anosov representations. Right, if you have a gamma hyperbolic group, rho a representation in G, you could always define things like limit maps, right? That was the important thing. So fix some opposite flag manifolds, f plus and f minus, And you'll have the same notion of transverse limit maps. Maybe we'll want to call them xi plus and xi minus now. Right? Well, xi plus is from the boundary of gamma to f plus. Xi minus, same thing to f minus. This is not squiggly enough to be xi. Yep. And from there, and transversality also, right? If you have eta plus different from eta minus, you want xi plus of eta plus to be transverse to xi minus of eta minus. Add your same adjectives, continuous, equivariant, and then you get the notions of limit maps. And now if you want to define the things that we also used, like dynamics preserving, this has the same definition. We'll take uniformly dynamics preserving at least. This will have exactly the same definition. You just replace the symbol transverse by the symbol transverse, and replace xi by xi, and that's it. It's this one. And the same goes for the flow definition of Anosov representations. Because of the way that we've been introducing these vertical derivatives on bundles, they work exactly in the same way, right? So I won't write the whole thing. I'll just say define Anosov representations from the flows, for example. So now you would have something which is you would have a bundle, but now with fiber instead of POV, you would have F plus, and you'd look at tangent spaces over some section sigma plus that you cook up from this limit map xi plus. Okay. And it's also equivalent to the to having uniformly dynamics preserving transverse limit maps. Okay. All right, so now what we are going to want to do is do the same thing as we have done before, constructing some axiom A flows, but with this more general setting. Okay, let's do the thing with without the discrete group first. So some flows over transverse flat spaces. And if you remember what I said at the beginning in the introduction of the very first lecture, which you probably don't, I barely do, we were trying to copy what was happening for the geodesic flow of the hyperbolic space, right? And what we ended up with was this L fibering over P transverse pairs in P times POV times POV star, and we had some flow acting on this, right? And we want to copy this now with a transverse flag space here instead, right? So you want to change your L, and this will be fibering over F plus transverse pairs F minus. Okay, it happens that there are now a lot of ways of doing this, whether here there was really just one possibility. And the reason for this is the dimension of the center of the levy. Let's see, I'll get the top board down. Okay, so how can you find such flows? So our requirements are that this L should be a homogeneous space, and that F plus, that it should have this flow phi t L that commutes with the action of G, and the orbit space should be exactly this. Okay, so now let's write our transverse flag space as some G mod L for some Levy subgroup L. And we want this L to be some G mod H. Over G mod L. So H should be a subgroup of L, okay, for this to be fibering here. And we want this action here, this flow, to be given by some sort of algebraic construction, right? There should be a one parameter group acting there. And I'll just give you the answer because it's I'll win us some time. It's a construction of associated bundles anyway. You're trying to construct a line bundle, well, an R principal line bundle over G mod L, and this is associated to characters on L. Right? And characters on L will be characters on the center. But now what we're going to be doing, because we want these to be R principal bundle and not S1 bundles, you'll have to look into R, the additive group here. So you pick a homomorphism from L to the additive group R. You define H, maybe have a sub B, to be the kernel of B. Right? And say B is not 0, so this will be a codimension 1 subgroup of L. Right? And now you can define a flow, so G mod HB will fiber over G mod L. So what you do to define a flow is you want to flow out the class of some G by multiplying on the right by some element X. You want X to not be in HB, right? Otherwise, this will be quite trivial. So what you're going to choose instead, X is in the Lie algebra, so you'll choose some XB in the Lie algebra such that B is non-trivial, so if you differentiate B at the identity at XB, let's choose it to be equal to 1. If B is non-trivial, you can always find such a thing. There are many XBs that work. There is one standard one. There is a notion of gradient here using the Killing form and trying to find this XB in the standard description. It will be finding it in some A theta. But this will it's actually not necessary to define the flow. Okay. So what we have to understand now is what are these homomorphisms from L to R, right? How can you really characterize them? So let's do the case of G as SLDR. Say F plus is the projective space, F minus projective space of dual. Right, so now your L will be blockwise diagonal matrices with one block of size 1. Right, so it will be something like some number A, some matrix G, such that A times determinant of G is equal to 1. Okay. So what are the homomorphisms from this to R? Well, it's a one-dimensional thing. If you pick, say, some number T, what you can look at is the map sending A and G to, say, log T times log of absolute value of A. That's one way. You could also put determinant of G instead of A. One is the inverse of the other, so it's the same thing. That's the only way of constructing a homomorphism from this to R. Right. So all the different flows that you'll construct with this example are just reparameterization by constant speed of each other. So that's why in this setting of SLD with the projective spaces as flag manifolds, we only had one flow. But now if you're moving to stay with SLD but do the full flag manifold. So F plus will be equal to F minus here, and be the full flag manifold, so just ones. Okay. Then your L will be diagonal matrices. So this is already almost R to the d minus 1, except from the signs, right? So here the only thing that you can do is take sums of such things, right? So this will be R to the d minus 1. So now you have a wider range of flows that you can construct from these G mod Ls. And the question now is like, which ones will give homogeneous, will give axiom A flows and quotients for Anosov representations? First of all, I should say that there are some of these flows that will work for any Anosov representations, but depending on your representation, you can look at different flows. So the last thing that I need to introduce very quickly would be the limit cone, or Benoit's limit cone. So this is defined by Jordan projections. Which we'll see as a map from the group G to A+. Just you do the Jordan decomposition of G, write it as some commuting hyperbolic, elliptic, and unipotent elements, and take the hyperbolic one, will be conjugate to something in A+, and that will be Jordan projection. But if you take G as SLDR, then so that we'll call it lambda. A lambda of G is just the decreasing list of logs of moduli of eigenvalues. And now you have a notion of, right here, the A plus means that A1 is greater than, they're in decreasing order or non-increasing order, and the sum is 0. Right. And the limit cone if you have a representation rho of gamma in G, this limit cone L rho will be the smallest closed cone in A plus, containing all the projections of your elements. Right? Okay, I'll try to get the statement on the board and finish there. The last thing that I'll say here is that you have this limit cone. Well, that really only makes sense when a rho of gamma is discrete. And when you look at some homomorphism B, so now let's go to the standard case. Like now, if you have B, a homomorphism from L theta to R. Right, so what we saw with this full flag manifolds case in SLD is that homomorphism from L to R is the same as the dual of A actually, like of the can be seen as linear forms on A. So you can identify this with essentially a log as now will not just be the dual of the whole A, but just the dual of some part of A. But there's a natural way of making it sit inside of A. So that the image of this A theta star in A star will be the subspace of A star spanned by the fundamental weights associated to the roots in theta. And okay, so this was just to say that you can define B of lambda of G for G in the group. And I'll finish with the theorem in this general case that corresponds to the SLN case that we did for the first 4 R's, which is that if you have rho and Anosov representation with respect to some opposite flag manifold F plus and F minus, if you add the extra hypothesis that B is strictly positive, sorry, that was just L rho on the Benoit cone, then there exists some M rho B hat, an open subset of LB, open rho invariant, flow invariant, such that, as you can imagine, the quotients, the action is properly discontinuous, and the quotient plays axiomally. Right. And this will be it. Yeah.
Can you give an example of a B that does not work?
Well, a B that is not positive. So, okay. Maybe I'll draw a picture. Say you have, I'll draw a bad picture. So say I'll draw the SL2 times SL2 picture. So say your A plus is the quadrant on the right. Okay. Now your limit cone will be some closed convex cone, actually. That's a theorem of Benoit. Rho. But now, if you pick a linear form on A, which is what this B will be, this B only has to be positive on L theta. So for example, if, say, the kernel of B is here, right, and B is positive here, this is okay, this works. If B were negative there, you'd just take minus B, and it would still work. So actually, the action is still properly discontinuous. Now there's something that works for any Anosov representation rho. Well, just take some B, which is positive on the whole A plus, right? And actually, one of these examples here, as this HB would be this group U that you had in Sam and Amanda's lectures. So what will not work obviously is if you take some B whose kernel will like cut the Benoit cone in two. Right.
So and in that case, do you know the flow is, I mean, do you know that this fails?
I would be quite confident that I mean, okay, so what would fail is the construction. It's like the M rho hats that we construct, the action will probably not be properly discontinuous on this. I'm not saying that there isn't another open domain somewhere where, but I highly doubt so. Yeah.
Yes. Do you need the limit cone to have non-empty interior for this construction?
No, because really what you're working with is the dual Benoit cone, and this always has non-empty interior. So non-empty interior is something that you get when rho is Zariski dense, but here no, we don't need to be Zariski dense or anything. And that's somehow important for me because something I could have said at some point is that there's a standard trick in Anosov representations when you go from SLN to the general case is to use representation theory. So usually you'll assume everything to be Zariski dense so that in the after using your representation as state irreducible and something. Here you cannot use representation theory because representation theory would only works for like these B's are some weights and it will only work for some integral dominant weights, but you want it to work for some non-integral weights, and so you really need to do it again by hand.
If you vary B, then like how different are these different domains?
They're pretty similar in the sense that they project to the same thing in G mod L. Yeah. So.
Are the flows orbit equivalent when you change your B?
Yes, yes, and so they're given when you're changing B. What you're changing is the period function of this flow. When you have a periodic orbit corresponding to an element gamma, the length of this closed orbit will be B of the journal projection of gamma. So that's what you're changing exactly. And they will be Gromov flows anyway, so they're all orbit equivalent. I mean, the restriction to the non-wandering set, but even if you look on the whole M rho hats, it will still be orbit equivalent. Yeah.
And I go back to a question. So you had the L1, which was a 2-to-1 cover of L.
Yeah.
But so what is the analog here?
You always have an analog of this. Cover of this. Well, there's always we're saying that cheating thing. If B is some corresponding to some fundamental weight, for example, you can always put this in a projective space and take the double cover to the sphere.
Yes.
That's what I don't want to do. And if not. You try to find an nice index to something with this, which I don't know. You might have something to do with your orientation here.
The thing is that these flag manifolds could very well be oriented in different directions.
The entropy of the flow is like you replace lambda 1 by b projective or something.
Yeah, the entropy of the flow will be like the exponential growth rate of the b of lambda g.
Questions? Right. Thanks again for the course.
Thank you very much.